Hello. So today we're not gonna do nuclear power. So today we'll be doing part 2 of the Navier Stokes existence and smoothness. Now, if you haven't seen part 1, you may be sure to watch part 1 because there's a lot of things that we have covered in part 1 that is going to be useful in part 2. Since I'm not gonna explain a lot of all the new concepts, like all the concepts to you again. So if you aren't sure about any concepts over here, be sure to watch part 1 for a much more concise and detailed study of some of these axioms, stuff like that. So today for part 2, we're going to do much more in depth and complex mathematical theories or slash or my self-created math, theoretical math made by me. So you'll see this blank part. So I'm going to choose a file. I'm going to get these up. So today we'll be talking about we're going to be talking about what eye rotation is. So I said detailed. No, I don't care about iCloud. So a much more in detailed explanation of eye rotation, which I find extremely interesting. Oh wait, hold on. Yeah. So I'm gonna rotate this. Give me a second. All right. Alright, so I got the pictures ready. So, today we'll be talking, I think I already said, eye rotation. So, I, which is square root of 1, let me see. Square root of 1. Oh, negative 1. Wait, let me try to find how to do the square root. Give me a sec. It's just gonna take a long time. Just spam the keyboard. Wait, I think I had the. Okay, found it. So, option V for any of you asking. So, option V. So, square root of negative 1. Now, rotation. Now, what is this rotation? So today we will be talking about this rotation. So this is a poster that I did for a math project. I know it looks scrappy and cheesy, but you gotta stay with me. So over here is a basic explanation what I is, and it's sort of like around the 11th grade, 10th grade level explanation of what I is. So very, very low leveled, and instead of college leveled, which is the main level that we will be using. So what is what is eye rotation? Now, eye rotation is the act of rotating planes, like rotating planes of waves. For example, if we have a wave of this, I already talked about this. So a wave like this is going to be rotated along the y-axis. So the axis that we are familiar of, which is the x and y, which let me draw it out. So this is the plane that we're used to when we're dealing with numbers. Oh wait, there's there's a table. So right over here we get the center of origin or 0. So let's duplicate this. So this part is gonna increase. This is the most basic principle while dealing with this. Well, these parts would decrease. Let me just type that. Now, give me a sec. This is gonna take a little while. So, so this is the plane of numericals that we're used to. Now, what is the I-axis? Now we have let's imagine that we rotate this. We rotate this plane until it is if measured in the second dimension is infinitely thin. So we're going to say that this is infinitely thin. Give me a second. So epsilon. Let's see. Oh, that's not epsilon. So let's say that oh wait, there's a hair on my trackpad. Okay, stand by. So let's say this is epsilon width. Now the size over here is it's the real numbers. So let's go over here. Oh, this is from last video. So let me just delete all of this crap. Okay, so now our plane, which includes all real numbers. So all real numbers to the square to square times 4, since there are 4 quadrants. So times 4. This is how the numerical plane is represented. Now, this has a width. So let's say it has width of epsilon, which is this. Which when rotated, which happens when the wave function, which let's call this symbol. So let's mark this symbol. Give me a sec. Really quickly, I'm gonna move this symbol. Okay, so this is a ret function. So ret x. So let me get a line. So this particular symbol is now called ret x. So keep that in mind. It's very important since I will be using that over here a lot. So the numerical plane has a width of epsilon, which happens when the wave function ret when ret is rotated using the I-axis by 90 degrees, or say the cos. So cos 90, which means infinite thinness of this area, which is represented via wait, this is wrong. So let's do this. So it is 1 divided by cos 90, which means epsilon, which equals to epsilon. There we go. So epsilon is basically the reverse of an infinity, or Or put it in simple terms, 1 over infinity. So let's find the infinity symbol. Yeah, there we go. So infinity equals to epsilon. And vice versa. So right now let's go back. This is so this is the plane, the numerical plane. Now, what does the I plane look like? So this is how the I plane would look like in comparison to the numerical plane. So this will be the I plane. Oh wait. So or let's say it's -1 plane. So made with the I-axis. Wait, autocorrect keeps autocorrecting. It's doing its job though. So I-axis. Now, so this is what the I-axis when implemented into a numerical system looks like. Now another misconception that in maths is that this is what the numerical plane would look like if relative to where numerical plane would look like. So this is what people mostly think of the numerical plane. Now, so this is another a folded up version of the plane. Since it won't look like this. It will actually look like this diagram over here. So x-axis and z-axis, where they have limits of these. So this would actually look like, let me just draw one up. This would actually look like this compared to the I-axis plane. So this folded up version is what the numerical plane or the double plane looks like. So it would look like this. So the negatives have their own plane. The positives have their own plane as well. So why is the I-axis in another dimension? Well, it's because since I is obtained via the square root of 1, so square root of 1 would look like as where there is -1. Let's say this is -1. So so this square would have the area of -1. Now what is the sides of a square with -1 area? Now this would be I, which would look like this. So I would have its own axes, and since this thing is not a 3D engine, let's just pretend for a second that the I plane, so let's say that this is the I-axis. I-axis would be over here, and while this would be flat compared to this. So let's say that this is the negative axis. So this is going to be negative axis, and this would look like wait a second, look like this. Oh wait, this is the wrong object to use. So let's see if I could just flip it around. There we go. It would actually look like something like this, which will be -1. So -1. So those will have an area of -1. Now, so since if you exclude this, if you rotate this cube into a flat surface like this. So let's get this flat surface. We rotate the cube onto a one flat surface, so only one face is visible. This would have a length of -1 over here. So give me a second. This will have the length of -1, where if you turn it into a square, which is the possible via rotating the cube onto the top face instead of the side face, you'll get, oh wait, it keeps jumping back to this part. You'll get something sort of like this. So you'll get a square which is made of -1. So this will have the area of -1, while its side lengths would be of I, since this is inside of the I-axis. So over here is the I-axis, and this would have the length of exactly I, where then this would also have the length of I, since it is a square. Now I might not be speaking that I might be explaining this in a very awkward way, in terms of such that I am a little bit stuttering, not fluent, because today has been a rough day. I just arrived home, and yeah, also because of this little masterpiece made by a very mischievous kid in my class. So this is basically what the I-axis is. Now, what is I-axis rotation? Now, this is completely another this will be a very so the I-axis is really simple to explain, but the rotation of the I-axis is complicated, since you'll have to deal with natural numbers and I being incorporated into a single superset. So basically, if you have a set of M, so let's say M is the, wait, let me find. So M is the superset of all real numbers, actually. And in this instance, we'll also have all imaginary numbers. So use I as imaginary. So Ri will be a part of this superset M. So M is going to be the superset that we're dealing with this time, which is a set that incorporates both imaginary numbers and real numbers. So over here, explanation done. I hope you can remember. If you don't, just skip to this part of the video, or and watch this again. So I'm gonna delete this. So now this part is what means. So this part is already explained. Now so this part will require some further explanation later. So over here is the I-axis, and this is what we just talked about, rotation of the axes. This is the viewpoint of any person who so happens to exist on the I-axis as well. So this will be the viewpoint of a person. Now, this viewpoint could be mapped out using when natural numbers converge into so basically 1 when converged into -1, or 1 converged, or I to the power of 4 converged to I to the power of 2, or I to the nth power converged to I to the nth power minus n divided by any number x, which for now can be represented as I-axis 1 converged into -1 multiplied or set as a matrix with n divided by x, so negative n divided by x. So what is n divided by x? So this basically means when a natural number or a real number converges into an imaginary number. So right now, the tilt of I, which is give me a second. So the tilt of I we represent as I tilt. So I tilt equals to the rotation, the convergence of I of a real number into I. So of an imaginary number, not I. Just as the imaginary number converges into a real number, this is the equation to represent the convergence. So let's explain. Let's dive into this deeply. So this part means the integral of a1, a2 on this square. So on the square, let's say that this is a1. So let me make some notation. This is a1. Give me a second. This is a1 and this is a, so, and the other corner that is the farthest away or the including distance on given plane, which is going to be a2. So this will mean the square, the integral of this square, which when given a contact point of an I point, which is a1i. So this entire thing proves the existence of I. So this part, it proves the existence of I, which will be very useful for Navier Stokes. So this I rotation and I plane is explained. So now time to prove I. So a1 to I points, which will be the square root of a1 to a2 to the power of 2 divided by 2 minus this then added up with, oh wait, I think this might be an error because this will cancel out with each other. So this is supposed to be these parts. So I might have messed up. So this will be this. It should be two corners over here. Well, this will be the other two Euclidean distance line. This will be the two Euclidean distance points deducted by another set, which then added up with the integral of I and a2. So which will be a2 to I to the power of 2 divided by 2. Now or wave function by the matrix of a1, a2, and xy. So x for the xy for the axes, and this matrix to contain the information of these corners. So I think this was supposed to be a1 to I, which is over here. So this will mean where I cancel out both, which both cancel out each other, which will basically mean this equation double integrated by this equation, then added up onto the wave function of what a plane would look like, or what a natural plane would look like when interacting with the imaginary I number. So on a I plane. So basically the merge of a real number plane with the imaginary plane, which will look like this. So this will involve hyperbolic spaces, which I'll cover later in the video. So this equation, which looks very fancy, basically means of all points of possible I points, which M will be a selected area. So x equals to the wave function of a plus bi, which means a given point on the hyperbolic space of real number plane with the imaginary number plane. So x minus wave function of 1 divided by 50 n to the n1, which this part means the resistance of the grid. So this will get into a little bit of physics. So this part means that if I were to be an arrow and this hyperbolic plane to be a fabric, so this analogy is used to predict what will happen if I is interacting. So the I axis is interacting with the hyperbolic plane, which means that this is the extra dimension, the extra point in which of measurable hyperbolic space is going to occupy. So basically, the occupants existence of I on this plane, which basically proves that that I. So let's say I in the hyperbolic space of over here. Give me a second. Hyperbolic space of I axis. So let's say that they share the same x axis. So ix squared. So ix squared y. Oh wait. So ix squared y would be divided by 2. Well, this will be exponent of 2, since we're dealing with hyperbolic spaces. So this will basically mean the hyperbolic space of real numbers and imaginary numbers of I. So keep this in mind. This will be the hyperbolic space equation. So this basically means to predict the coordinates of any I value that exists on the hyperbolic plane, which this part covered. So x would be the entirety of the plane. So the x would signify the wave function a plus bi, which means that if I exists, then I minus this wave function, which is supposed to represent the arrow hitting and interacting with the hyperbolic space, which means that when I interacts with hyperbolic space, it will be how do I explain this? So it requires this part. So when I interacts with the hyperbolic space as if in a interaction where there's physical interaction, like the arrow and fabric analogy, this part would mean so t 1 over 50. So this will mean resistance. So resistance via the passage of time and oh wait, I misspelled resistance. Resistance via the passage of time and this part, which means the wave function and given nature of the wave function. So why would the wave function create resistance as for time flow of the hyperbolic space? Now, so this will be the wave function. So the wave So the wave, let's signify with sine x. So like covered in last video, so let's say ret x. So ret x equals to the wave function. So over here, so this part would mean, so ret x of where, oh wait, the font has changed. So ret x is where the wave function creates resistance because of where a plus bi, which equals to the arrow, so the arrow interaction, where the arrow is infinitely thin and wide. So and has a length and has the arrow, or that is the shape of a line, a one-dimensional line, which means that this equation should be, so if it's traveling at the hyperbolic space over here, copy that, paste over. Oh my god. So over here, let's see if that happens again. Okay, it happens. So this, let's see. Yeah, it's broken. So a plus bi, then since there's already the I-axis over here, we only need to write down x to the power, oh wait, x to the power of 2y, which means the arrow interaction. Wait, how do I? Okay, x2 to the power of 2y, which equals to arrow interaction, where given arrow is infinite, has base area, so area, let's give it this of epsilon, since if it's is 0, it will render no interaction. Why? Because, so if, oh wait, the font, so if a2, so if a2 of, let's write down x to the power, so x to the power of 2 times y, which is the hyperbolic plane, minus the I function, since we already have I interacting, which eliminates the possibility of another dimension of I, or else it will be as if there are two directions where positives are the same. So if I were to be, give me a sec. So if the I were to have a existence on the hyperbolic plane, that it will mean something like, if there is a plus sign over here, plus, so on all 4 directions, no matter where you go. So this will be a completely useless graph, since so this will be a very inefficient graph, where there are 4 quadrants to represent a single quadrant, and inaccurate due to the impossible the knowledge of not knowing where lacking the knowledge of where you are, and due to interfering axes. So let me delete this. So this means that if I were to repeat over here again, where there is already an arrow or a segment of the y-axis, so let's say segment, seg, which could also be represented as where limit, let's write limit, where is it? So as x, so as the i-axis segment, let's say i-axis length, so this is the length, reaches infinity but never quite, which means that it is finite. So it's a finite arrow, which is not infinite. So finite arrow. So if only you could include this if the arrow was finite like this. But in this case, we're going to say that the arrow is infinitely long. So equals to infinity. So this part we're gonna say that the arrow equals to, so the arrow of the y-axis. So give me a sec. Y-axis will equal, wait, I'm having some technical trouble, stand by. So if y-axis equals to infinity, so give me a sec. Yes, so if this is this is the arrow that we're dealing with right now. So, and this is going to be our arrow. So limit y-axis equals to infinity. So if the area of the arrow of this hyperbolic plane will equal to so wait, I forgot this, AB plus I point. So we have to represent the point as, so let me find. So over here we represent the point as A plus BI. Now over here A plus BI is going to be the point and on the hyperbolic plane. So but we haven't said where the point would be, since different interactions would cause different scenarios, and this very very large equation shows us a predictable solution to every possible place where the ABI arrow would land. So this equation, let's say this equation we're gonna say as EQ. So we're gonna write the equation as this, or maybe I'm not gonna be this lazy. So give me a sec. It's gonna take a little bit while. So stand by, please. Give me a sec. Okay, so this would be the entire equation typed out. So so for the arrow, if the arrow's area of AB plus I of this equation of any coordinate calculated on this hyperbolic plane will equal to interference of I-axis where we're on the I-axis. Wait, I haven't changed the font over here. I-axis would include a superset. So let's make a superset right now. So let's call superset A would include A. So where A has, give me a sec, where A has the give me a sec. Is the superset of all of I with I with a fraction of the I axes. So we write x over here, which is wait, we don't write x. So we write a2 as the fraction. It will and so if a2 is larger, so if a2 is larger, so this is actually wrong. So if a2, give me a sec, of epsilon. So wait, of I think I messed it up. So 1 and a2. You feel free to skip this part as I get very frustrated. Okay, there we go. So as a, the superset is superset, which will be superset of this, which will be the superset of I and the extra part of I, which means that if a, so a wouldn't equal give me a sec, I'm gonna find the unequal sign, the not equal to sign. But not equal to I axes. So I axes. So this would mean that a wouldn't equal to I axes, which ruins the proof of I existing. So this entire part is to prove that I exist. So let me just delete this part quickly. So this is the equation of the hyperbolic space. Paste it in, and then this would be this will be like the equation for this will be the equation of why there's resistance via the given nature of the wave function. So I think I've gotten off topic over here. So it's like sort of off topic since I have transitioned to another explanation of another part of why I exists. So red x is where the wave function creates resistance, and a plus bi x to the power of 2 y that equals to arrow interaction if where a given arrow has a base of area of epsilon, which basically means that there is going to be resistance when the arrow collides with the fabric, and resistance before the arrow makes it onto the fabric, or the path when the arrow is on the path to the fabric, and also the resistance due to the infinite length of the I-axis, which why will create resistance basically is because this will require another type of math. So this is because that 1 over 0 would equal to an answer of, so 1 over 0 which will equal something of this scenario, which I proved that 1 over 0 using this equation will create resistance of double of that. That's the possible resistance of the arrow. So if the arrow was finite, it wouldn't have resistance over here, and the entire equation will fall apart, since without resistance over here, this would be this point where it interacts, and the prediction of where the point can interact and produce given result is going to be illegal. So we'll say that this is equals to 2, since it gives double the resistance of a finite line. So why to why have a resistance? Why have resistance of this? So the resistance, I just explained why we have it. So also there was a problem with my previous equation. So 1 over 0, then minus 1 equals to 1, which proves indicates that if so it indicates that if there was finite I-axis arrow length, then the resistance would be 0, which causes the I rotation, which causes the possibility of I rotation. So I-axis rotation, I-axis rotation to collapse to infinity, which we don't want. So this is basically our formula. This is basically why we have to have resistance. And that's it. I think you'll know what I rotation is. Very simple concept. A very, very simple concept that I could fit onto an A3 poster. So this is a very shortened example of what I rotation is. Like, why didn't I do an expanded example? Expanded example basically talks about why there's rotation, but in this video I explain why there's rotation and also why there is this part. Oh wait, there's still something I need to tell you. So what is the flex of this? So the flex equals to the free amounts of degrees, so the gradient amount of degrees that I could rotate this thing on. So the gradient of let's find gradient. So the flex of I rotation, I-axis rotation, let's turn that into that. So flex of I rotation is going to be a gradient of, let me find the gradient. I need to find that little triangle. Okay, the gradient of so since if you have, so since the I-axis is infinite as mentioned in previous examples, so I'm gonna write a limit sign. So over here, where do we get the limit sign? No, where's the limit sign? Wait, I'm close. There we go. Limit of where x is going to be our I-axis equals to infinity. So let's just get infinity over here. The gradient of all possible flexes, which is this part. Now let's say that the point is AB plus I, and this part is going to say this part is going to be x equals to, let's do the So x will equal to any will equal to the point. Wait. So oh, this is wrong. I have to change this part. So x, so this will be infinity. Since we have an infinite amount of points to deal with, so this will be infinity, and x equals to ab plus I. The arrow over here, let me see if I can find it. Oh, it disappeared inside of that part, so I can't paste in that much, or else it's gonna delete it. Okay, so will equal to hyperbolic space over here. So hyperbolic space deducted by these parts, so it's gonna be ix, where it's gonna be infinity to ix. Now we might have to include hyperbolic space in here, since we're talking about the flex of an eye rotation into the parts of natural area, so of of real number plane. So it's gonna get this one. Please work. No, it doesn't work. So it's gonna be this I x to the power of 2. Give me a sec. Y to the power of 2 to the power of 2 divided by 2. So will equal to, this will equal to x plus 1. So any points, so this part will also equal to, so let's just make, so this part would also turn into, also be the same as if a superset, let's call it Q. Let's call it superset Q. The superset Q would contain all of these points. So superset Q would have subset of, okay, so of this. Ah, my god, no, it doesn't work. So contain this again. So this superset will contain this part. Let's just try again. No, it doesn't work. So yeah, basically this superset contains this part and also the gradient, which will be this. So yeah, so equals to, so has the flex. So that's basically it. So I hope you enjoyed this video. I remember, so still remember this part. Wait. So still remember like page 2 where I asked for the prediction of what you think the equation is. We'll be talking about it later. So sorry, you're gonna have to wait another video for the explanation of that equation, since I forgot. Or maybe just maybe tomorrow, after I come back from a mathematical competition. So that's it, glass houses. Goodbye. Have fun. I wish you had fun watching this video. And yeah, that's it. Bye.